So I'm going to go a little quickly through some stuff, and then I'm going to have you guys look at a few problems that are like the problems that are in your first homework set from chapter 1. We're going to go through this really pretty quickly. Maybe I should put this up here just in case. Put it up here as the book, in case you don't have your book yet. Well, I mean, the first thing we talk about is functions, and hopefully the basic idea of a function doesn't get anybody down. When I first teach functions, what do you think the biggest mistake people make is? When I first teach it to like my Math 90 students, when they see a function f of x. I'm not going to use that because you can't really, you can sort of see that. Yeah, the divide by f, that kind of thing. Okay, so we shouldn't have any trouble with that. Oops, that's chapter 2. Blah, 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 blah. Let's see what page it is. Sure. All right. Well, this will work out all right, I guess. So functions, when I first teach functions, this is not necessarily 100% true, but it's a good way for people to start off. I say a function should be able to model something that can happen in real life. So I can't have a baseball that's here and there at the same time. So it kind of leads into the idea of a single input, like at 5 seconds, the output would be where the ball is, unless some samurai say, break the ball. But somebody always brings that up, or I bring it up. But it's a good idea why we want to define something as a function, not just a relation. Why do we make this extra requirement for the subset of relationships, functions? I'm not going to spend a lot of time in this section because this should be old news. The definition of function leads into what kind of test graphically to tell something's a function? Careful now, that's later. Vertical line test. And that just comes right off of the definition, which sounds very much like it's from Highlander. For every input, there can be only one output. Right? I'm showing all my geekiness to anybody who knows what the hell I'm talking about. Blah, blah, blah. And that eventually leads into, I'm getting a little ahead of myself, but the whole idea of an inverse function, what is it you test to see if something's an inverse function?
If it's a one-to-one.
If it's one-to-one, and how do you graphically test that?
With a horizontal line.
Horizontal line test. So instead of, to be invertible basically means that once you flip that bad boy over the y equals x line, it has to still be a function. So of course, if I took a parabola and flipped it, it would not be a function anymore. So, but somebody said, why flip it and then check? Why don't we just leave it and check this way? Basically flip our test. So that's why horizontal line test checks to see if it's one-to-one, checks to see if it's invertible. Okay. So that stuff should be old news. Domain and range should be old news, that would help. Can you guys see that? Let me zoom in a little bit here. Let me ask you a real quick question. This doesn't have a scale on it, but I don't care. You can at least see where they're trying to be. Can anybody tell me what, let's say this is a graph of f of x. Anybody tell me what f of 1 is? What is f of 1? Yeah. How do you know it's 3? You don't even have a function. What magic are you doing? Deduction, I like it. Well, be more specific.
Because when we move 1 unit on the x-axis, we move 3 units up on the y-axis, and that's the function.
To locate the point, I love it. Because what do I do? What do you do to graph a function? I give you a function, you put a point in, you get a point out. Together, that makes the point. So you not really put points in, but you put the x in, you get the y out, and that's exactly where you're going to be. So this is the opposite of that. This is somebody who's already plugged points in. So you don't have any work to do. So you've got to see the output for 1 must be 3 because that's where the freaking point is. Right? For some reason, I always get people that don't quite understand that, but let that be that this is a representation of all the outputs for every input that's in the domain. So f of, what else can we tell easily? That was the one thing I could tell easily. Well, f of 0 is 1, right? And what's the domain of this function?
0 to
2, 3, 4, 5, 6, 7, yes. And the range?
Like
negative
2
or negative
2, 3, 4, yeah. I like it. From negative 2 to 4? So, well, it looks like it goes a little bit over, but I'm not being all that picky right now. Okay. This should all be old news, but please slow me down if I hit somewhere that's a little weird. Make sure that about. Oh, how would I find the domain of this function here?
Should be more than 0.
So I won't let you use your graphing calculator to do it. And be more specific.
Under the root should be greater than 0.
Or,
Equal.
I like it. So the way you do domains always is you say in English what the restriction is. The inside of a root that's even root can't be less than 0. Therefore it must be at least 0. So then you write that in math. If the inside must be at least 0, the inside must be at least 0. It's almost silly. That's how domains pretty much always work if they give you the function. You solve that bad boy, right? If I gave you this function, what do you got, Jeff? Sure. How would you get this guy's domain?
Well,
Just
The
factor it.
denominator should be greater or equal to 0.
Careful.
Can't be
well, we
0.
said
Good.
equation does not equal to 0. But
Not the whole thing could equal 0. It equals 0 at 0. Good. So the bottom cannot equal 0. So the bottom cannot equal 0. And then you solve. Right? All right. So I want that out of the way right now. So that's a little thing you learn early on, but I don't know if anybody puts it that way. That's all you got to do is say in English what the problem is. What would create a problem, and then write that what you just said in math, and then solve it. Cool. Okay. Of course, I can get more disgusting functions in there, but they basically rely on the same idea. Now, here's the second thing that troubles people about functions. Not only do people try to divide by the f or the g, but they also have trouble with inputs for some reason. So, when they first learned it, I don't think you guys should have too much of this trouble. So if I say that's my function, and I ask somebody, all right, well, what's f of a?
2a minus 1.
That's what it is, but of course they just, I'm not sure, but it's because they're not really sure what the parts of this mean yet, and it's really just the dummy variable is what we call it. It doesn't matter what letter we use, it's just tradition to use x to start with. So this would just replace that with that. And of course, if I say f of a plus h,
2a plus h.
yeah. And of course, the mistake I always get is somebody tells me it's 2a minus 1 plus h. They just kind of throw the plus h at the end, which is neat. It just doesn't work. Yeah. And then you can simplify that. Okay, cool. So that's the kind of very simple function work you have to be able to do when we get into our first major concept coming up in chapter 2, which will be the idea of limits. Limits are going to rule our world for a little while, and then suddenly they're not. So we're just going to live in limits for a while. You'll have to be able to do stuff like this for limits, and that's not difficult stuff to do. So if now here's the interesting thing. In this first one, can somebody give me what the point is that this thing goes through? That's a very strange question, I know, but I don't care.
Can you repeat the question?
Based on what I've written here, what's the point that I can write down that's illustrated by this function input-output?
1 over 0.
Negative 1.
So for example, if I said this, what's f of 1?
0, 1.
2
1. So what's the point associated with that? 1, 1. Right? So if I say, what's f of 0? Negative 1. So the point associated with that is, because that's my input, that's my output. That's my input,
So it's 2a minus 1.
that's my output. With me so far? Okay. And then, go on. The point here,
A plus h. 2a
2
plus h
equals
minus
h
1.
minus 1.
cool, I'll just go ahead and do that. So, notice when they say, do you see up there where they say f of a plus h minus f of a over h? Do you see that?
Yep.
There. This is going to be, I want you to realize, that's a question that very often shows up in algebra books, like in Math 110, or even maybe sometimes pre-calculus, they'll do this. Just because you can do this at a level before this. But we're going to do more stuff to this, of course. And really, fundamentally, where the hell does this come from? This is just y2 minus y1 over x2, get in there the right way, minus x1. Right, because of course there the a's disappear, that's why there's only an h on the bottom. Are you guys with me?
Yeah.
So this is just a reformulation of the slope formula, but specifically for not just any 2 points, but whatever point this is, this has to be h away from it. Whatever input that is. Are you guys kind of with me? So it's very interesting. So it's really what this shows then is at a, it's somewhere, and then at a plus h, a little bit away from a, it's possibly somewhere else. So if we do this, we're just going to find the slope between those two. Is that cool? Now the function itself that I started with is a straight line. So of course the function itself does this. But I can do this no matter what function is here. You guys agree? It's a good idea. So if I plug stuff in, what do I get? On the top I'll get the y's difference. And right there, this is another thing that screws people over. When I'm subtracting two things, the second guy's got to go in parentheses, of course. Be real careful about that. It gets really freaky very quickly if you don't do that. Because basically, whenever you do this on almost every function we're going to look at, a lot of stuff should cancel. It's got to. Not everything, but most things. So of course there I get my 2a's cancel. My negative 1's cancel. Is that cool? So I'm just left with 2h over h, which is 2. Not surprising, because we just said that this is the slope. It's y2 minus y1 over x2 minus x1. This is a stupid line. And we know the slope already of the stupid line, right? So then you're all like, good God, it's a long way to go for that. You guys familiar with me? Now, I do this a lot. I've gotten way ahead of where I really this, but this is calculus. This is the first major thing calculus does, is it says, well, we could just look at the damn thing and see the slope from algebra. But now I've got this more general idea that can attack any function and give you something. I don't know. You got to figure out what that thing is. Okay. All right, that's enough of that for now. So that's going to be stupid important. Okay, so here they're just making sure you could do the... So here they have a quadratic, and they do the same kind of stuff, and they end up with this expression. We have no idea. Now somehow that should relate to a slope, right? Because that's what this thing does. That thing just evaluates slopes. That's what that thing's job is to evaluate slopes. Okay. Oh, yeah, blah, 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 blah. All right, so there's a lot of blah, blah, blah. So, you have a whole range of mathematics that deals with fit. This obviously is used a lot. Anybody take statistics? All right, so you know exactly what I'm talking about. Correlation, regression line. So fitting data to a line so you can make extrapolation, so you can kind of interpolate where it's going. Or very often, like in physics, we did this cool thing where you put some material in something and you send X-rays through it and you see what comes out the other side, and it kind of forms this shape, and you can fit it to known shapes of known materials. You can figure out what the hell the material is. If you ever wondered how the hell, here, send this to the lab, figure out what it is. What the hell does the lab do? I'm still alive. It's not poison. So this is one thing they could do with this material, is to bombard it with X-rays and then see what the shape is at the end, how much energy gets through, and compare that to known shapes. So that's another place where modeling data would come in handy. Blah, 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 blah. Oh, and this kind of thing, this problem here, when we get to calculus word problems, which just, sounds way cool, you'll have to be able to do something like this. Shouldn't be too evil. So they'll tell you exactly this. Has a volume of 10 cubic meters. The length of its base is twice its width. Material for the base costs $10 per square. Blah, 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 blah. So you have to first figure out, where do they have it? The volume is 10 cubic meters. So somewhere here they've got blah, blah, blah. Where do they have it equal to 10? Here. There. So there's the volume of it equal to 10. You can solve for H. Doing everything in terms of W. So, this kind of thing should have happened in your pre-calc class where you had too many variables, so you had to solve one thing to plug it into the other thing. The same kind of thing happens in calculus. And mainly because we're in what's called single variable calculus. Now later there's of course something called multivariable calculus where you just kind of go at it. And you don't have to worry about getting rid of everything. But we're not going to do that yet. Blah, blah, blah. Let's see. Vertical line test, all this old stuff. Piecewise functions. There's the answer to my question, but what is a piecewise function? Why does it exist?
Because there's a hole in the graph.
All right, well, the hole in the graph comes from the way they defined it. But can somebody give me a physical situation where you would need a piecewise defined function? What does a function do? So if I have a rocket take off, a function can model where that rocket is. Now what could happen right there?
Explode. Shoot down.
And then you have some other function take over. Right? You can have some catastrophic failure, and then it just the engines die, and then physics take over and it drops. So you had one function here because of the thrust, and there are all the other crap, the resistance and all that stuff, and the weight of the thing is becoming less, and that's a great physics problem to screw. So you got one function doing this, and then something can happen here, bah, engines die. So then another function takes over. So to me, that's the basic reason why a piecewise function would be used in relation to something in the real world, right, which is a good place to start. But of course, there's other things for piecewise function, like there's a heavy side function, where you have one function turn on at a certain point. So it's sort of like flipping a light, even though it's not instantaneous, it's decent to approximate it as instantaneous. Are you guys kind of with me? The current goes from 0 to something stupid quick, so it's like a step function. Blah, blah, blah. Blah, blah, blah.
Mm-hmm.
All right. Not too concerned about all that. Okay. So in this one you'll see, domain range questions. This first section should not be a big deal. If you want to go this a little quickly. This goes through some of the basic models, so linear models, that should be no problem. Blah, blah, blah. Good Lord, linear models forever. Polynomials, yay! So you just should know the basic look of things. You should know what 1 over x are hyperbolas. This isn't going to come up a lot in this class, but you should know rational functions where it doesn't exist, asymptotes, things like that. Limits. You should know the 3 big things. Let me ask you guys, what could happen with horizontal asymptotes? I'm looking at you guys who've taken pre-calculus. What are the 3 situations that could arise when you're looking at horizontal asymptotes?
When y equals 0.
Well, there's one situation that would lead to y going to 0.
Would it be like a bigger power on the bottom?
So it's all about if I have a bigger power on the bottom, for example. And let me say this in a different way. I think I did this in my pre-calc class because it helps you get ready for calculus. I don't know if you guys wrote it like when x goes to infinity. Does that look familiar? What does y do? Yeah, because the bottom power is higher than the top, and you can divide by the highest power and all that kind of crap, right? You'll get there eventually. But the shortcut is highest power is on the bottom, so it's going to overwhelm the top. Right? The bottom's getting bigger faster than the top, so the whole thing's going to 0. Right? So a better way to write that would be the limit as x goes to infinity. Let's call this f of x, so I don't have to write the whole thing over. Of f of x, 0. I don't know if any of your pre-calc teachers wrote that. It's not a bad idea because we're going to be living in limits, swimming in limits, breathing limits, eating limits, loving limits. It's not a bad idea to have a preview of them, right? So you see, this means that does it ever get to 0? No, because I can never get to infinity, right? But it looks like it's going to 0 as my inputs get really, really freaking big. That's basically what it means. So a limit handles a situation where I can't get to something. It says, all right, you're not going to plug that in. You're just going to say it looks like it's going here when this guy is going here. That's the basic job of a limit, right? I always think about it like the movie The Blob. I would not be like the guy that just reached down his hand. You get really close. You're like, what is that? You just don't get right on top of it because I don't want to. So a limit lets me, and the limit that I get really close, it's freaky. So I'm going to back away. The second situation would be if the powers are the same. So what would this be? Good. So the powers are the same, so they're both growing at the same rate. So the limit's going to be 2/3 when x gets really, really big. And then finally, if it's like this, it must be the power on the top is bigger. The limit would be... Good. It's got a slant asymptote. So the limit here would be infinity, but it's going to go to infinity by following a slant asymptote. How do you find a slant asymptote? Long division. I love it. So long divide. Cool. It's going to be x plus some crap, right? So it's going to follow some line to infinity. Does that sound all familiar? All right. So we're going to kind of do a harder way of this, and I'm going to point out every now and again, oh, you can just pre-calc that. You can pre-calc that. It's good to verb orders. Pre-calc that. So you can kind of shortcut the process, because you already know this. You should. So you shouldn't have to do a lot of work to tell me something that's obvious from your last class. Okay. Well, let's see what. Trig functions, of course. So bone up on your trig if you need to. The look of exponential functions, the look of logarithmic functions, of course, those two are inverses of each other. Okay. I don't want to spend a ton of time on this, but you should be aware, this doesn't show up overly often, but it does, it's actually sort of a back-end deal. I don't know how else to explain this. Calculus very often will back up into a situation like this, and then we can explain why we get a shape without a location. Because the slope right here, for example, you guys see what I mean by that?
Yeah.
The slope, like, right at the top, what would the slope be right there? 0. Is that cool? You guys just did calculus. That's crazy. Calculus is just finding the slope of any curve anywhere. That's all calculus does. So here the slope is positive, goes 0, goes negative, right? Is that, you guys see that? So here the slope is 0, and here the slope is positive, here's negative. There it's well, actually, those aren't the same shape, are they? Here they are. Same shape here, so that's more of a stretch. So it's going to have the exact same slope here, right? So if I had a function that, if I gave it a slope, it would work back what the function was, it wouldn't know where to put it. Because all it knows is what the slope is supposed to be. It doesn't know where it's supposed to sit. You guys kind of with me?
Yeah.
So this idea of transformations actually kind of works on the back end of what comes out of calculus. Calculus says, use the shape. I don't know where the hell to put it. So that'll be interesting when we get there. But here, you guys should know how If I have square root of x plus 5, you should know that goes back 5 on the x-axis, stuff like that, right? When you first learn this, it takes a little while for that to kick in. But when I teach my students this, I try to tell them, because the first thing people want to do is move it over 5, because you see plus 5. You're like, what the hell, Jeff? I should go 5 over. And then I say, no, when you put something in, it could be 5 less than it had to be before. So here it is before the shift. Here it is after the shift, right? So to get 0, I had to plug 0, and now to get 0, I have to plug negative 5 in. It can all my inputs can be 5 less than they were before. That's why you shift back. So whatever way you know it, you should know transformations. Blah, blah, blah. And these are stretching, or stretching it or compressing it. You normally see that a lot with trig functions. You do that with trig functions. The phase shift in the period of trig functions, right? And the amplitude and all that kind of stuff. Okay? Some guys are humoring me. Sure, man. Alright. Blah, 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 blah. Composition functions. I don't want to spend too much time on all that stuff. Got it. This talks a little bit about graphing calculators. I'm hoping that... I can't remember now. Did I put up there a graphing calculator?
The inner one?
No. The little guide for you guys. No. I do have one. Let me put it up there. In case you haven't used it much. Any guys never really used a graphing calculator much? Okay, a few guys. Less and less every year, because now it's getting harder and harder to stay away from them. So I'll post on here a little guide for basic functions on the graphing calculator. And anytime we hit a procedure that I'm going to expect you to be able to do in the graphing calculator, we'll do it together. Up here, I've got a cool little go away. Graphing calculator emulator. Pop. So that'd be nice. Ooh, neat. There's some calculus I think is left over for me. All right. They're doing some calculus there, that's why it's shaded in. All right, that's enough of that. So whenever you hit that, I'll do some examples up on there. Okay. Exponential functions, I really hope we have no big troubles with those. We should know our rules of exponents. Let's see if there's anything interesting here. What's the base of the natural log? No, not what's the notation for natural log. What's the base? E. And what is E? You want to hear what the really cool thing is? If you have the graph y equals 1 over x, and you go from 1 to some number, and you look at the area here, do you guys see what I'm saying? The area that you get if you go from the x-axis up to the function. To get this area to be 1, you have to go out to e. It's kind of a cool, like the letter pi represents what? I like that, but better, because you can never finish that out. If you want to go that way, you have to tell me the whole thing. You don't want to go that way. So tell me, pi is the ratio of circumference to diameter, because c equals pi d, so pi equals c over d. So that's where it first came from. People said, no matter how freaking big a circle is, if I divide it by its diameter, I always get the same damn number. What the freak? So everybody thought it was from God and all this kind of stuff. So they gave it the letter pi, because it's a neat thing. So the E comes out of several situations. To me, this is one of the coolest ones where it comes out of. It also comes out of, let me see if I remember. I think that's it. If I let n get really big, this is kind of weird. What happens inside here? If n gets really, really big, what happens here? For those of you at home. Yeah, so what's the inside go to? 1. Does it ever get to 1? No. What's the power go to, of course? Infinity. 1 to infinity would basically be 1. Forgive me my putting infinity in. You normally don't do that, but basically 1 to infinity would be 1. But this never gets to 1. So it's not going to be 1. There's got to be some number in between 1 and infinity. That's a little bit of room. So that actually comes out to be e. It's neat. It's just weird shit. And mathematically, these two things are actually related. And I'll show you that when we get to that point, when we do the calculus associated. Okay. Okay. And we got inverse functions. Again, I really hope that's not a big deal. Please, they're not. Okay, let me go. I want to get to the problems for your first homework set someday. So they ask you some conceptual questions. Oh, this is 160. No way. Just to point out, just make sure everybody understands what the first assignment is. There's a concept check and a true-false quiz. I'm just assigning that because this is your review section. And then there's a little just straight-up nuts and bolts problems to do. I'm hoping our little discussion, you'll see stuff like estimate the value of f of 2. So everybody should know how to look at that now. You have some translation problems and some drawing of inverses. Why does this thing have an inverse?
Because it's 1 to
1
1.
to 1 why?
Because it passes a horizontal line.
I love it. Sweet. It doesn't kind of come back on itself in terms of horizontal line. I like it. Transformations of stuff. All right. So I know I went very quickly, and I skipped a lot of stuff. And I did that on purpose, obviously. Oh, I don't like this. All right. I've never actually done this. Just use the ebook up here, but I figured I'd give it a try. So I want to do a little bit out of chapter 2. And then we're going to call it quits a little bit early. Don't get used to that. First day, I figure you suffer through me talking about the syllabus and then stuff, and I don't want to kill you the first day. I'll leave that for later. So the very first section, I think we're going to give up on that. It's going to drive me crazy. Kind of talks about the idea of limit from a little bit different direction. So here's the problem. Let's just look at the problem itself. So right here. Find an equation of the tangent line to the parabola. Y equals x squared. Okay, so first off, tangent line. What the hell is that supposed to be?
It's a line touching just one area or one point of a thing.
And that definition sort of suffers a little. You can see on one of their examples. If I wanted to touch just once there, it's eventually going to touch again because it kind of curves. But I let that go. It's very strange if you try to define it that way because you have to say in a certain neighborhood of the point because you don't care that it hits again over there. The main thing you want a tangent line to do is if this was like a ball on a rope. Somebody was swinging it, making this weird-ass curvy shape, you with me? And then they let go of it, pop! It would be the direction the ball would fly in, right? It's the old thing about swinging it over your head, and if you let it go at the right place, it's going to go forward, go around somebody's ankles and trip them, right? I don't know what weird movie I have in my brain. So the line, if I see it, if I think about my, this axis is time very often, even if it's not, I just say, here, as it's moving along, it's positive slope, like we were saying earlier. But what I'm doing is, at this point, there is some slope associated with that point. Because it's if I didn't keep it on that curve, if I just let it continue in the direction it's going right then, it would be a straight line. There would be no forces making it curve. You guys kind of with me? Yes, sir?
Is that like centrifugal
Yes.
force?
So it's very much like physics. And I'll often couch my remarks in physics because no matter how weird physics gets, it's still real world stuff. So it kind of helps us see what is mathematically going on. How we do it so far? Does that make sense? At every point, it's going in a certain direction. The minute it goes, so right now, so it's moving along, and right now it's going to go there. So it goes there. Now it's going a little bit more up. So then it goes, every single step it takes, its slope is changing. So calculus has a really difficult job. Calculus first wants to figure out what the slope is at every point of any curve. And it's changing every single infinitesimal step. It's changing. It's like, whoa, shit. So the tangent line at any given point just has to be the line that hits it once, going the same direction as it is right then. How are we doing so far? So you do run into some troubles, like if I had a cusp. This really freaks out because everything we're talking about here as far as tangent lines go seems to be related to the slope of the function. So what happens right here to the slope of this function?
It dies.
Zero.
It doesn't die, it's not zero.
It's a straight line.
There's no one answer for that.
Yeah, there's no one answer because it's different. Over here it's positive something, and then instantaneously it's negative something. So maybe here it's maybe right there, right before the cusp, it's going like it's 2. And then right after the cusp, it's going like it's -2. You don't want to be in that car or that plane. And that's serious whiplash. Not good, right? So calculus craps out right there, and it's not calculus's fault. It's because from both directions it's not lining up. It can't talk about slope because here's the connection between algebra and calculus. In algebra, what do you need to find the slope?
Good point.
Now, what's weird about calculus is I wanted the slope at a point, right? So algebra says I can find the slope between any 2 points you give me. And calculus says, all right, I'll give you 1 point. And then algebra says, what the hell did I just say? But the way we get around it is interesting. We let there be 2 points, and we let them get closer together. And that's the way around it. That's why we first talk about limits. Okay. So coming back to this problem that shot me off on that tangent. So let's try to recreate what they did up there. Normally, if I get this kind of problem in algebra, it's not going to be tangent lines or something. It's going to say it's parallel to this other line that goes to this point. Remember those problems? Find the equation line that does all this crap. So here, I know I'm at the point 1, 1, but algebra cannot handle that. I want a slope, or even better, this dude. Doesn't matter. I want a slope to plug in there, and to get a slope, I need 2 points. So what we say is the other point would be some other point. And of course, what's y in this case? Let's be even more specific. What's y?
X squared.
X squared, 11. How are we doing so far? No answer? Okay. I'll take that as a good. So let's go ahead and set up the slope formula. What would it look like? The slope between those 2 points. And you should be past the point where you're like, we don't have 2 points. Yeah, we do. Alright, so the book calls this point, let me do it the same way they do. Blah, 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 blah. Oh, here we go. So they call this P, they call this Q. So the slope between P and Q would just be
X circumference. X minus 1.
cool, right? And I don't know if they make the discovery, of course, that you can do something nice with that. They should. No, they don't. Too bad for them. We'll go along with the way they do it because in general you won't necessarily be able to always reduce what you're looking at. And in fact, it's not illegal to reduce this because again, the only way to get a slope, and this is what I really want you guys to understand, the only way you can get a slope is to have 2 points. Calculus wants to know the slope at a point though. So what gets me around that is the idea of a limit. Because the limit never gets there. So I just say in the limit that these 2 points distance goes to 0, what's the slope? So at every step I have 2 points, right? Do I ever get to the point, do I ever get to the input 1? Do I ever get there? No, so that's why it's okay to actually reduce this. But let's just not. Let's do it the way they did, because it's more generally true. You're not always going to be able to factor and reduce. So we'll just keep it this way. So, how can I use this to get there then? What I do is I use points near 1, 1 to kind of complete this expression. So, I could use, who knows, x equal to 2 to start with. That's not overly far away from 1. Now, you'll start to realize, if I have a function like this, then 2 is pretty close to 1. But if I have a function like this, then 2 is freaking far as hell away from 1. You guys understand? Sort of like the idea of resolution and that. You know? In this case, we have a nice function. 2 is not crazy far from 1. Not a bad place to start. So what's the slope in that case?
3.
Well, let's just say m2. Yeah, so it'll be 3 over 1, so it'll be 3. So then what we do is we step a little closer. So we start at, we really want to know 1, 1, what's going on at 1, 1. But we start at 2, 4. That's horrible. That's too bad. And then we step a little closer. So then maybe we go to 1.5. Right? So if I make this for x equal to 1.5, we step a little closer. What do we get for the slope? Yeah, you'll get, what do we get? 2.25, 1.25 divided by 0.5, so 2.5. I like it. Cool, right? So do you start to get the idea? This is going to happen to you throughout this section. Throughout this chapter, the first section comes at it a little bit differently than the other ones do, but the same idea of stepping closer and closer and closer. So then you can take x equal to 1.001, get really, really, really freaking close. Right? Now, what's the problem with what I've done so far? There's one little problem if I just sort of stop there. When I say getting close to 1, I've sort of half-assed it, in a way. Because I got close to 1 this direction, I didn't get close to 1 that direction. So it's really an idea of both sides to see where they agree. Now, with a nice function like x squared, you could probably get away with just doing one side to see where it's going. But the whole idea of this is to get a pattern. I want to see, what does it look like it's going towards? That's exactly the idea of a limit. So let's do a 1.001. Somebody help me out. What will my slope be if it's 1.001?
2.001.
2.001? So I would feel really comfortable to say that it looks like if x goes to 1, my slope is going to go to 2. Right? You can just double check it by going from the other direction. X equals 0, x equal to 0.5, x equal to 0.999. Do you guys see the symmetry there? Is that cool? Yeah. Approaching 1, the same amount for both sides. And they can really double check the pattern that you think. This is definitely not perfect, because the answer might be 2.00032. Oh, shit. Right? So this has definitely got problems. It's not good enough for us, but it's a good starting place for the idea. It's just like, it's exactly the same thing as, what way do you learn to solve this first? How do you want to solve this?
Elimination.
No, believe it or not, you got to think back. First thing you learn is, of course, the idea behind this, which is you graph the two lines and you see where they meet. What's wrong with that approach?
It's not exact.
It's not exact. What if the answer was 1.9999332? I'm not going to get that from my ugly ass drawings, right? So, do you see the analogy here? This is good for the concept, and we're going to do a lot of this, more than you want to. Really good for the concept, but then we start to see its shortcomings. So then we got to develop some more algebraic way. So here, Really good for the concept to graph them and see where they meet. Shortcomings, they can't do everything, so we come up with an algebraic way to do it. Right? More computational way to do it. Okay. Let me see. Blah, blah, blah. So, I think a good thing to do is to look at some problems. And see if we can all understand what they're trying to get from us. So number 7. Can't remember what I assigned, but look at number 7 there. Let me blow that bad boy. So, what is average velocity? Because, you take a trip, and you can stop somewhere, you can slow down somewhere, you can speed up really fast somewhere, you can do all this shit. But overall, you can just ignore all the weird things you did in the middle and get an average velocity for the whole trip. And that's really what's going on here. We have some funky line doing stuff, and I want to know what the slope is right there. So I kind of just do a slope between 2 points. I ignore all the curviness in the middle, and I just go directly from one point to the other. So it's really what average velocity does. So when they ask you to find the average velocity, what is another way of saying slope? What is slope really?
Average change.
Change. It's a rate of change.
Delta y over delta x.
Beautiful. The change in y divided by change in x. It's a rate. So it could be meters per second. That's a velocity. So when they say velocity, they're really just saying the slope of this function. So if I want to know the average velocity for the interval 1 to 3, don't make too big of a deal out of this. How do you find that? Remembering that velocity is another way of saying the slope. What are my points that I'm using?
1 and 3. 1 and 4.
Yeah, it's good. So at 1 second it's 1.4. At 3 seconds it's 10.7. So you're really just finding the slope between those 2 points. You with me? So very often it's just a matter of translating what the question is into what the hell you want me to do, right? Average velocity is just total distance divided by total time. That's really all it is. But you can even look at it simpler than that. It's just freaking slope. So total distance I've traveled would be the difference in these two distances, which is what I'll get when I do the slope here, right? That'll be how far I've gone, divided by how far it took me to go that far. Beautiful, right? Connection, sweet. So all these problems, easy as hell. You agree with me? All right, do them. And then I want you to see if you can get part B. Push.
So in this case, the slope should have units.
Exactly. Good. So that's one thing I was going to see if it happened. But anytime I ask you for a physical situation where you have units involved, you're going to see a lot of ratios, of course, when we do these things. So your units have to reflect that. And units are going to become really huge to understand how to figure out what the units are supposed to be. Leibniz notation actually makes it easier to figure out what it is. So when we get there, I'll show you the connection. But here, obviously, all the units on this has got to be what? Yeah, meters per second. This is going to be velocity. It's going to be the positions over the times. So you can look the answers up in the back of the book if you haven't. All right? I don't know. It's pretty simple, right? I just want to make sure everybody. What did you guys get for 1? Sounds right. 2? 516. Yep. 3. Okay. 4.
7.
Okay. Cool. Now, part B. What do you think you can do there?
You just take the averages of the answers.
Average of what answers?
Each of your slopes.
If you want to know at 3 what's going on, if you know the slope from 2 to 3 and you know the slope from 3 to 4, you could actually average those two slopes. Now that's taking a lot of liberties with what this function really looks like, but it's okay. We're just looking for an average. We're just trying to get an idea, right? Somebody's a little bit better, and I don't know if this, let me see if this makes sense to you guys. So I have some function. It's obviously, it's obviously doing that. So there's some slope from here to here. There's some slope from here to here. That's what we found in part 2 and part 4, right? Slope from 2 to 3 and the slope from 3 to 4. So you have both sides. This is not a pattern kind of problem, then. You can kind of average those out to see what's going to be a 3. There's even a little bit better thing you can do. And it actually comes out to the same number in this problem. It doesn't always. If I wanted the slope at 3, I can do the slope between x's 2 and x's 4. And that'll actually approximate the slope at 3 pretty well. You guys see that?
Yeah.
How we doing? Now again, it all depends on, these steps I'm taking are relatively small because I have a nice, well-behaved, smooth function. If I have a function that goes like that, this is way too big of a step. Step 1, maybe there's 18 billion oscillations in the middle. Who knows where you end up? You with me? It's a nice, smooth function. I could do this. So if I want to approximate 3, I can look at the slope between 2 and 4. As look at the slope between those two, you just take that minus that over that minus that, and you get 6.3. Okay? And you get the same answer if you average the slopes you got here and here. You should. Are you guys with it. So I want to show you an example of a problem that wasn't quite the pattern looking one. But you do have problems that are just all about finding the pattern. Like this one here. See how it goes 1.5, 1.9, 1.99? You get closer to 2, and then it gets closer to 2 from above. You guys kind of with me? And then you just see what if you get like if your answers are 4.7, 4.8, 4.83, 4.89, I don't know. And then over here you get maybe it's approaching 4.9. You look at the pattern from both sides. Maybe this would be 5.2, 5.1, 5.0, 4.91. It looks like it's going to 4.9. So it should be semi-obvious where it's going. You guys semi with me, okay? Maybe. Okay. So the last thing I want to talk about, just to keep my promise, I'll let you guys out. Like stupid little early. A whole 5 minutes. The very last thing I want to look at is on page 89. What you got? So early. This problem here. And this actually gets to the heart of what we just did. So this says, and I've already kind of discussed the idea of what this is. So if I let t go to 0, so see how they go to 0 from both above and below. And they do it in both directions because it's symmetric. Right, good old even symmetry. So you get the same outputs on both sides. You can kind of see where it's approaching. Right? You might even suggest maybe it's 1666666, but you don't know for sure. So they're like a fail images. That's the kind of problem, that's the kind of work you'll do in a few of the problems on the previous section. You with me?
Yeah.
You'll approach something from both sides, you'll see a pattern, and then give me what you think the conclusion is. Where does it look like it's going? This is a lot like a problem I gave you on the pretest. What is the main problem to figuring this out for that? It's almost too easy of a question. Why can't I just figure that out directly? Like,
You can't have the 0 when
exactly.
it's common.
If I had this question, please let that be easy. What's the limit as x goes to 1? 3, because I could just plug a 1 in. Right? So the limit normally is used for something I can't get to. If I can get to it, just plug the damn thing in there, right? The limit is like, what the hell are you asking me about? Plug the damn thing in there. So this would be 3. I can't plug a 0 in. So there's a nice algebraic way around it. You can do it this way, which is like graphing equations to see where they meet, which is insane, if the answer is anything off from an integer. Or I can actually do a little algebra and try to kill the problem. What algebra can I do here?
Conjugate.
Good. Multiply by the conjugate. Now, in algebra, we normally rationalize the denominator. And it may be somebody said something about the numerator, or here's a good example of where I want to rationalize the numerator. So what would I multiply by?
P squared plus 9.
Plus 3, good. So the conjugate. So on the top, that's just a difference of squares pair. I get t squared plus 9 minus 9. Very interesting. And then at the bottom, I get t squared times crap. Never distribute that, because right there you can see what's going to happen. So this is t squared over t, kill that. So it's 1 over, wow, that's really awesome. That's another reason why we should stop this, because it's like it had some kind of aneurysm. So I get that after simplifying a little bit. So what's the limit as t goes to 0?
1/6.
Yeah, if I put a 0 in there, I'm allowed to do it now. Why? Because my problem, the thing that was in the way of me plugging that in, I killed it. So if you do a little algebra like factoring and canceling, problem gone, that kind of thing, right? So here you plug a 0 in, you get 3 plus 3, you get 1/6, which is of course 0.16 forever.
I'm just confused with why is there 1 top and not 0?
Oh, because t squared divided by t squared is 1. Yeah.
Okay.
So you can never get a 0 through division unless you had a 0 to begin with.
Right.
Cool. All right. So we will have a lot of problems like this, but I want you to know there's an algebraic way around this, thank God. This does get to the concept.